All right, so as I was saying at the end of our previous video, so that was the end of our preparation for the exams. There will be then some short videos on other topics that are not to be covered by any of our exams, including the final exam, but they might be of interest to some people. So one of them, for instance, when we talked in class about Euler's theorem, Fermat's theorem, we can view this from a more, say, conceptual point of view as a phenomenon that happens in groups. So very quickly, what's a group? If I have a set G and then a set of elements, it could be numbers, could be functions, could be, say, matrices, 2 by 2 matrices, 3 by 3 matrices, whatever. If I have a set of elements and I have an operation, say star. It's like addition or multiplication of matrices, whatever. The only requirements are that there will be a group, provided several things happen. And first of all, if I take 3 elements, A star, B star, C, there's no, so for any A and B in the group, I require that when I compose them, when I multiply them, we'll just call it multiplication from now on, but it's not multiplication. I just say A times B instead of A star B. A, B needs to belong to this. But if I have 3 elements, I can do this in 2 different ways. I can multiply them in 2 different ways. Like these two together, A times B, and then the result times C, or A times the B and C. We require that this is the same. So we can associate them any way we want. This is more important than to us that this operation is commutative. So this is not an important one. B star B is equal to B star B. Because there are so many structures, algebraic structures, where this doesn't hold, but this does. So this is a more basic axiom. Okay. And then we require to have one element that acts like a zero, how zero acts with respect to addition. If you take 0 plus any number, it's that number, or 1 with respect to multiplication. So let's call this E. There is one element E such that E times any element X in the group is equal to X times E, and it's equal to E. We require that this happens. As soon as we have this, then E is uniquely determined, because if I have 2 different elements that satisfy this, like another one, E prime, let's call it, or D. That's the primes, I don't know if are visible, these commas. And so let's say D times X is equal to X times D, and is equal to, E times X is equal to X times E, and is equal to X. And this is for all X in G.
Okay.
So, for instance, if the group is the group of integer numbers with addition, E would be 0. 0 plus X is equal to X plus 0, and it's equal to X, not. With respect to multiplication, E is 1. So, 1 times X is equal to X times 1, and it's X. But if I have 2 elements in the same group satisfying this, they have to be the same element. Because you can compute, for instance, E times D, and on the one hand, from the first relation, E times D, if I take X to be D, E times D is D, X to be D. So this is D. But from the second relation, if I take X to be E, E times D would be X, which is E. So you see that D has to be equal to E. Why prove that there is a single 0, the single 1 with respect, when you can prove this immediately for any group at the same time? Okay. So this neutral element is uniquely determined in the group. And we require another thing, that any element has an inverse. for any x in the group, there is a y in the group such that
x star y,
x
y is e.
is equal to e.
Yeah.
Right.
Yes.
Y star x then is equal to e.
Okay.
And again, so we require that for each x there is such a y. Now it's very easy to see that there is only one y. If this happens, then for all x there is an inverse.
Mm-hmm.
There is a unique inverse. Let's see how we prove this. Suppose there is another one like z. X times z is equal to, say, z times x, and is equal to e. Then what we do is, let's compute the following. X, I have to be careful in which order I put them, but x times, because this is not assumed to be a commutative group, but x times y times z. Let's just compute this element. We can compute, as I said, in two different ways. We get the same thing. E. So, on the one hand, I can write it as z times x times y. And on the other hand, this is equal to, I write it here, z times x times y. Well, first I compute x times y, and then I multiply by z. And if I take z times x is e. So this is equal to e. So this whole thing on the left side is just e times y. But then what the properties of e times y is y. Z times x is that element for any element. So e times y is y equals this, e times y equals this whole thing. Equals z times x times y, but x times y is required to be e. So we get the z times e, but z times e is z. Well, the properties of e. So then we get that y equals z. Like this. When we discussed in our class, okay, inverse is modulo a prime. When we said there are really many inverses, like what's the inverse of 6 modulo 11? 6 times, maybe 2.
2, yes.
6 times 2, it's congruent to 1 mod 11.
Yeah.
But 6 times 2 plus 11, 13.
78.
Is 78 is also congruent to 1 mod 11. So how come we have two different inverses? Well, we have two different inverses because if I look at the set of the entire set of integer numbers, they do not form a group with multiplication modulo 11. What forms a group is the multiplication of numbers that are relatively of residue classes, of congruence classes, modulo 11, and relatively prime with 11. So they form a group. So in that class, so you see, 2 and 13 are in the same class. So as a class is the unique class. So the classes form a group, not the numbers. Okay, not the numbers. We are representatives for the classes. Okay, so the classes form a group. You can multiply two classes, two congruence classes modulo 11, or you can add classes. Now, if you add residue classes or congruence classes modulo 11, we have 11 classes. They form a group, and there are 11 elements in the group. Each element is a congruence class, mod 11. If with addition, with multiplication, this set is no more a group. The zero class doesn't have an inverse. If I remove the zero class, I'm left with 10 classes. Yes. Those 10 classes form a group. Each one has an inverse. The class of 6 has an inverse, which is the class of 2, or the class of 13 is the same class. Okay. But let's talk about this just a bit later. So we see that if there is an inverse, the inverse is unique. Yeah. Once we see this, we have this simple proof. We don't have to prove it in every single case. The residue class is modulo 11. Each class has a unique inverse, or in other contexts. We know. As soon as we know that it forms a group. Now let's see some groups, some examples of groups. Suppose I work modulo 10. How many residue classes I have modulo 10? 10 classes. The class of 1, all numbers that end with a 1, like 1, 11, 21, 31, we put all these on. Now, say work mod 10, to make it simple. How many congruence classes? I have 10 classes. The class of 0, the class of 1, 2, 3, 4, 5, the class of 5, the class of 6, the class of 7, okay, the class of 8, the class of 9. That's it. The class of 10 is the same, is identical to the class of 0. And let's recall, what was the definition of the class? It is a set of elements itself, and it's the set of all the integer numbers that are congruent to 1.
Mod 10.
Mod 10.
Yes.
All those that are congruent to 2 are here. Now, if we look at these classes, they form a group with respect to addition. You can add any class, any two classes, you get another class. You have associativity, you have this neutral element that's 0, and each element has an inverse. The inverse is going to be the opposite class because it's with respect to addition. So the inverse of the class 5, it's something plus, because our operation is plus in this case. Plus, so 5 plus 6. 5 plus 6 is 0, because it's 11. Okay, so with respect to addition, I have and if we want, we can make a table like this, a multiplication table. Put the classes here, the same classes here, and add any two classes. It's very easy with addition. Let's do multiplication. But if I do multiplication, they do not form a group. Multiplication of these classes is indeed associative. I do have a neutral element as a class of 1. 1 times anything is that number. But it's not true that each class has an inverse with respect to multiplication. The classes that have inverses, and in general, numbers that have inverses modulo 10 are those numbers that are relatively prime with 10. So let's see where those numbers are. And I claim that those numbers are exactly in 4 classes. 1, this class, consists of numbers relatively prime with 10. 1, 11, 21, 31, 41, and so on. That's one class. This is another class. Numbers that end with 3 are relatively prime with 10. So in other words, numbers that are not divisible by 2, numbers that are not divisible by 5. And what I'm saying is a nice thing happens, and it happens all the time, and in general, that these numbers that are relatively prime with 10, so for a class, for any class, either all the numbers in the class are relatively prime with 10, or none of them is. There's no possible confusion. In this case, for instance, the class of 2, this consists of numbers like 2 plus 10 is 12, 22, 32, and so on. None of them is relatively prime with 10. All of them have the same, all of them have 2 as a common factor of 10. And also negative numbers in this class. 2 minus 10 is negative 8, and so on. All of them are even numbers, they're not relatively prime. So that's not a class. So we can say the class is relatively prime with 10. And then it means that all the elements in the class are relatively prime. Or the class is not relatively, this class, for instance, is relatively prime with 10. You can check all the numbers are relatively prime with 10. So, how many classes I have that are relatively prime with 10? Well, that's exactly how many numbers I have less than 10 that are relatively prime with 10. 1, 3, 7, and 9. So in other words, Euler function gives me the number of classes. Yeah, because those are the number of numbers less than n, relatively prime with n. So what we get now is a group for any n, for any n, we get a group that has exactly Euler function element. Group with multiplication. Multiplication of classes. All right. So now let's see one example with 10. I look at those classes that are relatively prime. Let's make a table. Multiplication table. So this is mod 10, and we have a multiplication. The star is dot, is multiplication. Classes are 1, 3, 7, and 9. Okay, 1, 3, 7, and 9. When we multiply two numbers that are relatively prime with 10, none of them has 2 as a factor, none of them has 5. So the product is still relatively prime with 10. So no wonder if I multiply 2 of these classes, I get one of these classes again, relatively prime with 10. So 1 times each one is 1, is that one. 1 times 3 is 3. If you recall how we multiply classes, we just multiply these numbers and we take the class. 1 times 7 is 7, is the class of 7. 1 times 9 is 9, the class of 9. For multiplication of numbers or classes, multiplication is commutative. So 1 times 3 is the same as 3 times 1. 1 times this is 3, 7, 9. But I need to recall this thing. I need to put classes here. Then 3 times 3 is the class of 9. 3 times 7 is 21, is the class of 21, which is the same as the class of 1. Mm-hmm. And 3 times 9 is 27, so is the class of 7. So you see, when I multiply by 3, I get the same numbers, but in another order. That's what happens in a group. You take a group, say a finite group, I mean a group with finely many elements, because we have infinite groups, like with addition, you can take all the real numbers. They form a group. You can add the numbers, subtract them. So, there's infinitely many elements. But if we take a finite group, a group with finely many elements, and I multiply all the elements by the same element, I'm getting again all the elements of the group, but in another order. This was a key fact in our, when we prove, say, Fermat's-Little theorem or Euler's theorem. Now, 7 times 3, 21, class of 1. 7 times 7 is 49, is the class of 9. 7 times 9 is 63, is the class of 3. The same here. 9 times 3, 27, class of 7. 9 times 7, 63, the class of 3. And 9 times 9 is 81, is the class of 1. Now, if I take, as I said, so this is the complete multiplication table of multiplication of residue classes modulo 10, residue classes that are relatively prime with 10. If I take the class of 7 and I multiply all these classes by 7, I'm getting all the numbers in another order, all the classes in another order. So let's just take this. 7 times 1 is 7, the class of 7. But I can interpret this in terms of congruencies, if I want. So 7 times 1 is congruent to 7 mod 10. 7 times 3 is the class of 1, meaning it's congruent to 1. Mod 10. 7 times 7 is the class of, where is this? This is the class of 9, or in other words, for us, if I multiply classes, I say the class of 7 times the class of 7 is the class of 9. Or if I work with numbers, representatives for these classes, 7 is 7, it's congruent, not equal to 9, mod 10. And the last one, 7 times 9 63 is congruent to 3, or in terms of classes, the class of 7 times the class of 9 is the class of 3. And this is mod 10. We saw this earlier in one of our classes. When we saw an example of Euler's theorem, why is 7 not 7 to the 9 like in Fermat's-Little theorem? No, 7 to exactly Euler function. There was 7 to the 4. If you remember, we multiply them and I get the 7 to the 4 here, times these numbers, 1 times 3 times 7 times 9, it's congruent to the same product, 1 times 3 times 7 times 9, in another order, mod 10. Then what we did, we canceled this congruence, we canceled this factor. So 3, 7, 9, because we can do that, because they are relatively prime with 10. That was the key reason why Euler took this, right? When he proved this relatively prime, now we can cancel, and we're left with just 7 to the 4 is 1. 7 to the 4 is congruent to 1. Mod 10. Or in other words, in terms of classes, the class of 7 multiplied by itself 4 times gives us a 1. Now this proof works in general for general groups, but let's just do it in the case of commutative groups. A times B is equal to B times A. Clear? This was just multiplication table. Mod 10. That's why I wanted to talk about this, not talk about groups in general, group theory, big theory in itself, but just to see the connection with what we did before when we worked with Fermat's theorem, and also with Euler's theorem. And we remarked at that time that hey, the proof is the same. And what I'm saying now is actually the same in any group, or let's say any abelian group. So suppose I have G is a group, and the elements of the group are, I don't know how many, say it has K elements, I don't know how many. Let's call them somehow. X1, X2, Xk. These are not variables, it's just a notation for those K elements of this group. Now if I take one of the elements, say B is one of the elements in the group. So B is one of the xj's, I don't know which one. What I'm saying is that, well, let's say G is abelian, which means commutative. It's a commutative. Just simplify the proof. In the interest of time, I've just worked with abelian groups here. Means x times y is equal to y times x. For all elements, x and y in the group. Okay. Then what we can do is the following. I take these elements b, x1, x2, xk, and I multiply each one of them by b. So b times x1 times, star, if you want, whatever the group operation is. I should put it like this, star. So the group has this structure, one operation that looks like this. Okay, b star x1 is an element. I don't know which one is this. Let's call it A1. B times or star x2 is equal to A2, and so on, all the k elements. B star xk is equal to AK. All we know by the fact that this is a group, this is assumed to be a group, is that these are elements in the group. So A1, A2, AK are in the group, but we don't know yet that they are different. So we know that each one of them is an element in the group, so each one of them is one of those xj's, x1, x2, xk. Now, I say that our claim is that these are distinct. A1 not equal to it, and so on. Or how I say this, they are distinct. A1, AK are distinct, and each one of them different. elements. Distinct. Why is this? Suppose that's not true. So suppose I have two elements that are the same. Say AI is equal to AJ. Or to simplify, let's say A1 is equal to A2. Doesn't matter, same proof for anyone. Say A1 is equal to A2, so don't complicate this. Is equal to A2. Now I come back here, and let's see what we can get from this. Now if A1 is equal to A2, I can maybe write up to this. Oh, okay, this is a billion. I can write right here. Say A1 is equal to A2. This means that B star X1, because this is A1, is equal to B star X2. So now I use the main property that we discussed. One of the main properties in the group. There is an inverse for each element. B has an inverse. So now we multiply by the inverse of B. Both sides. So I have B inverse star B times X1 is equal to B inverse. I denote it like this. B to the minus 1 is just a notation for the inverse of B. B inverse times this expression is B inverse times star this expression. X2. Okay. So now we use associativity, so we can rewrite this as B inverse star B, and then star X1 is equal B inverse star B, like that, and then the result star X2. But B inverse times B by definition is just E, the neutral. So E star X1 is equal to E star X2. But now, if we call what was E, the property of E, E star X1 is X1, then E star X2 is X2. So X1 is equal to X2. That's false. We took the elements of the group to be different, as exactly K elements. Okay, false. So the conclusion is that we cannot have A1 equal A2, and the same for the others. So indeed, all these elements are distinct, and because I have a set that has K elements in here, and these elements are distinct, and these elements, each one of them belongs to the set, but no two of them are equal. It follows that these K elements are exactly those K elements in another order. So now we just multiply them, and I multiply them, and I get B star X1 times B times B. I'm not going to put the stars because then it's going to be too long, but they are there. What I get is Bx1, meaning B star X1, times B times X2, times B times X3, and so on, times B times Xk is equal to this product, A1 times A2 times AK. But we saw that these numbers, not numbers, sorry, these are not numbers, they are elements in the group. They can be anything, they can be functions or whatever. We don't care about the nature of these elements. These are the same as X1, X2, Xk, but in another order. Now I use the fact that this is a commutative group, so I can put them in any order we want. A1, A2 is the same as A2, A1. So this whole thing is just X1, X2, and so on, up to Xk. This part, I can also rearrange. I can take all these B's to the left. How many of these B's I have? Well, Bx1, Bx2, Bxk, I have K of them. So what I get is that B times B times B, K times, as a notation, I just say B to the K. It's just notation for B composed with itself, or star B, star B, star B, K times. And then X1 up to Xk is equal to X1 up to Xk. Oh, so now we can cancel this. How do you cancel in a group? You just multiply by the inverse. I multiply both sides by the inverse of Sk, I got rid of Xk. I multiply by the inverse of Xk minus 1, get rid of all those up to this. And when you multiply each one by its inverse, you get E. So we get b to the k is equal to E. And this is the generalization of Euler's theorem. I'm not going to write it as a theorem, but that's the idea. Take any element in the group, and you multiply it by the rule of the group by itself exactly as many times as the size of the group, the number of elements, and you get the neutral. Again, in the case of Euler's theorem, the group is, you just take numbers modulo any given number n, you take those relatively private n, we have a group that has Euler number, phi of n elements, and therefore any element to that power is the identity, is E, but E in our multiplicative case is 1. So that's why the product is 1, or the b to the k is congruent to 1 in our case. Not all groups are commutative. I just wanted to give an example that I have here. Just an example where I have the keys, my driver's license, whatever. All right, this thing. Let's see. I'm not going to write anything. Let's just look at a few minutes. If this particular video is not too long, do I have a few more minutes?
Yeah.
All right. So we have a cube that has 6 faces. Each face has 9 little squares. So 6 times 9 is 54. I'm not talking about a group that has 54 elements. No, I'm talking about a huge group. These squares are not the elements of the group. The elements of the group are movements, are permutations. Like, for instance, one element of the group is this. Or I do it like this. Another movement is going the other direction. So, like x and x inverse. If I don't do anything, that's the identity or the neutral element. This group is not commutative. For instance, let's see, it's not the same thing as doing this, say A followed by B, or B followed by A. It's a different permutation of this. So this is a group of permutations. Now, if I have 3 elements, or 3 numbers or 3 whatever chairs, how many ways you can permute? So how many permutations? Exactly 3 factorial.
Yes.
The 6. If I have 4 elements, then I look at the permutations. Going to have 4 factorial 24. Now, if I have 54 little squares, the number of permutations is 54 factorial. It's an incredibly large number. All the permutations of a set that has 54 elements, they form a group of permutations. This group is not commutative. It's highly not commutative. As we saw, I have to say this is a subgroup of that group in the sense that it's still huge, the group of permutations that we can do, but not all the permutations of these 54 little squares can be done. For instance, no matter how I move this or like that, I cannot take a central square and move it to the corner, unless I use a hammer and I break it, which did happen. Not to me, but other people did this to see if they can rearrange it in a different way. But not possible. In the corner, anytime you make a move like this, a piece a square that's in a corner will move to another place that's in the corner. So in a group that's not abelian, not commutative, if I take any element A and I multiply by a B, it's not necessary. I don't necessarily get this equal to B times A. What I'm saying now is that one way to check is to compute A inverse, B inverse, and see if this is or is not the neutral element. If the group is abelian, A times B is the same as B times A, so you can interchange those two. Then you get B times A inverse times B inverse. Then A and A inverse sit together next to each other. Then that's why they cancel. And then once they cancel, then you're left with a B and a B inverse, and they cancel. And it gives you the identity of how it was denoted by E. So in other words, this is E in the group, if and only if they commute. So to check that these two operations, an A and a B, don't commute, I can just take A inverse, say A, B, A inverse, B inverse, A, B, A inverse, B inverse, and I got a mess. This is not. But there are good. Now let's see what do I do with this. I have to remember what I did last. What I did last, I unfortunately moved this like that, and probably is this, and then most likely, I have no idea how to repair this.
I can solve it if you need to.
You can solve it, eh?
I swear I can.
Well, I have no idea how to solve a thing like this, but because we have a volunteer here, you can do
It'll
it.
take a little bit, but yeah. You probably
All
have
right.
you probably have to pause the video for a while. Yeah.
Very funny. No, we're not going to pause the video. We'll solve it, and we show the people that we can actually solve it. I was going to say another thing after he's working on this.
We're gonna have to like put a time that like people can skip to because it's gonna take a video.
No, because I wanted to show something else. So it's totally fine. Well, after so many hours of helping me here, it's no wonder that all of us are a bit tired. I was going to say the following. There are commutators like this, expressions of this form, A, B, A inverse, B inverse, that are very good operations. I let him work, let him do what he wants. I'm talking about expressions of this form, A, B, A inverse, B inverse, that are good in the sense that they do not commute, but the product is very close to being the identity. And one of them I was going to show. Now, for instance, another one that is of this type is if I do, and I wanted to show you another operation. It's A, B, C, D, A, B, C, D, A, B, C, D, E, A inverse, E inverse, D inverse, C inverse, B inverse, and no A inverse I have. So see, it's A, B, C, and A, B, C, D, and E, and I get their inverses, but I don't have in the proper order. That's another nice operation that we can show there. The fact that this is the same as that, or of exactly the same type, even if I have more elements, can be seen as follows. If I denote in my group X to be, say, B, C, D, E, then the inverse of X, X inverse, is not B inverse, C inverse, D inverse, D inverse. It is exactly in the opposite orders. E inverse, D inverse. Okay, thank you very much. Right on time. Good. D inverse, E inverse. What am I saying? X inverse is, you have to take inverses from right to left. E inverse, D inverse, C inverse, B inverse. And then if I look again at what this means, I get an A, followed by B, C, D, E, that's an X. Then followed by A inverse, and followed by E inverse, D inverse, C inverse, B inverse. This is exactly the inverse of X. So, inverse of X. So it's again an expression of this form. Now some of these are very bad, like what I did earlier, and then we need an expert here who can solve this for us. Some of them are good, like this. A, B, C, D, E, A inverse, E inverse, D inverse, C inverse, B inverse. So we'll go like this. Let's say A, B, C, D, E, and then A inverse, E inverse, D inverse, C inverse, B inverse. That's what we have there. Almost everything stays as it was, except for three of these was going to take a chair. But
Oh,
yeah, that's fine. That's fine. Just for this. Yeah, no. Let's sorry. So then I can show the cube right here. Except for these three. So you see, if you look at these faces, you have a white face and a blue face. There is exactly one central piece here that is blue and white at the same time. Just one small little cube. Okay, that has two faces that are colored, one in blue, one in red. Now, if I look at three faces like this, blue, red, and white, there is exactly one corner that has three faces in these colors, red, white, and blue. Okay, so what happens when I do this operation? I have these three pieces, these three small cubes move around. I obtain a cyclic permutation, order 3 if you want. So the green and the yellow one moves up here. The yellow, the red and yellow moves here, and then the red and green, moves there. So if I apply this operation again, if I do it properly, what this is still a permutation of the same three elements. Same three cubes, as you can see. But if I apply one more time, of course I have to get back to where I started. Okay, so there was something of order 3. That's an element in the group that when you multiply it by itself 3 times, you get a neutral element. The funny thing is, all these moves that are available are moves that have order 4. Their order is 4, like this. You move 1, 2, 3, 4 times. Each one is of order 4. Now, if the group was commutative, everything in the group to the power 4 will be the identity. But because the group is not commutative, strange things are happening. Like that permutation that we just saw now has order 3. Another thing that is order 3. If I want to interchange the centers, I will do the following. Again, it was an A, B, A inverse, B inverse. And all these centers are interchanged. There's something again of degree 3 or order 3. I will do this one more time. And when I do it a third time, I will get back to, hopefully, to this. The operation we showed earlier is it's very good when you want to solve this, because it tells you that you can take a cube from anywhere and you move it around and you put it in the right place. Now, we don't have time now to go in more details into this thing, but that's the general idea how you solve it. Maybe we should stop this so we can talk about other things.